Okay, the way this class works, um, if you miss class or you don't have to take something, you watch these videos, all right? Blah, 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 blah. And some people wonder, like, how can I maybe do a little bit better in some of these things? So here would be one way. Actually, when it comes to designing notes, for the most part, if I have time, I will read the chapter. That's good for the video, isn't it? A little sinus thing going on there. All right. And I read to set up what, okay, it's called Chapter 5, Apportionment. I don't know what that means. No idea. I mean, I could kind of make a guess what that term means as far as, the English of it. So what I do is I just take a quick read. And actually this book is actually very cool for this as far as getting you to understand the term. Now I'm asking, probably it took me 10 minutes to, son of a nutcracker. Okay, it takes me 10 to 15 minutes to read the beginning of the chapter, the two people that they talk about each chapter, and then all of section 5.1 up to the homework. And I don't do any writing. I don't get my notes organized yet. I just read it. And then after I'm like, oh, this is easy. I understand what apportionment is. So those that claim, that this is hard and we're not doing, well, I've already identified a lot of things that I see going wrong here. I put keys online and I see people just verbatim copy the keys. I'm missing a page. They're missing a whole page. I make a mistake on the key. They make the exact same mistake on the key. That's one problem. The other problem is not taking that 10 minutes I'm not even asking. I mean, you don't have to do it, but it's not really asking a lot of you. So if you really want to understand what we're doing, I think we need to do that and actually read these. With all that being said, I will share with you what I got out of the reading. What I got out of it is this one little story about a company that's for real. You see this building. About trying to, I may jack it up. You read it again. This was not the most important reading. But about assigning offices for X amount of people, but there's more people than offices. So how do we fairly distribute the office space? So, of course, we can't put one person in one office if there's more people per office. So how do we fairly divide that up? Even more importantly that I got out of the reading, you can read about these guys. I think it's kind of cool that they're math geniuses, if that's the appropriate term, but then dedicated part of their lives to figuring out apportionment problems fairly. All right, how to divide stuff fairly, and quite complicated. So again, would we go that far? Probably not, but that's all that it says. So it gets a firmer idea of what apportionment is. But then I think what the coolest thing that I learned today, I'm trying to find it right here. I did not know this, and you probably know this better than I. I thought the House of Representatives probably changed, I guess, in my mind from every 10 years when a census comes. I thought it was a set number of, if you have this many people in your state, you get this many representatives. And it's completely wrong, according to this book. What we have is a fixed number of 435 representatives. And then what happens is when we get a census every 10 years, those are divided among the states. So essentially what could happen after 10 years, if Illinois' population goes way up and New York's goes way down, we may end up getting an extra representative or two. And then that makes us more powerful in votes that are designated, that are voted on in our Senate, let's say, or whatever. You know what I'm saying at this point. Not a history person or a government person. So I found that interesting. And then what I also found interesting in this reading is there's different methods of doing these apportionment problems. And a different method does, in fact, change how the apportionment works. So, of course, in government, if you have a certain idea and I want more representatives from my state, you would probably want this apportionment method and compared to this other one. And historically, these have changed. And just this one reading, how they do this apportionment problem has changed from decade to decade. And a lot of politics are involved in that. So with all that being said, again, this is a 10 to 15 minute read just to get you an idea of what's happening here. And then when you know what's happening, then you have a better idea of figuring this stuff out. So there we go. Apportion, definition. Assign as a due portion to divide into shares which may not be equal. Okay? So an example that I just went through, just for your purposes of hearing me say something. Yeah, the House of Representatives, given to each state, this is how this is taken care of through apportionment. And every decade, it may change how they figure this out. You're going to find out 2 ways to do an apportionment today from 2 different historical characters. Okay, so problems arise when one or more of the due portions has a fractional part. Probably a better word for this is a decimal. They use the term fractional part, but we're going to get decimals when we do our math. So we do have to be aware of that. Okay. So, can we divide a person? Can I take 0.4 of a representative and put it in this state and 0.6 put it in the other one? It doesn't work that way. So what we have to do is figure out a way to figure out how to get these fractions fairly divided out. All right? So let me stop for a second. I just did the stupidest thing ever. Again. All right, here we go. All right. So, apportionment problem. Before, I thought this was all frozen. You didn't get to see me do all that erasing. You didn't tell me to hit save. Thanks a lot. All right. Now I saved it, so now it's ready to go for 6 hours. Well, okay. So apportionment problem is determine a method for rounding a collection of numbers so that a sum is unchanged. And we'll talk about this, kind of relating it to the United States, but then make a smaller country that only has 6 states, as you can see in the situation here. Okay. Now for this particular question, we are going to talk about what the standard divisor is. Okay, what we have to do is this, though, before I talk about the standard divisor, and then talk about how it works with the House of Representatives according to the numbers at the time the book was written. We have a state of 6, or a country of 6 states. First thing we need to do, which is kind of annoying for this question, is get the total population. So we have to add those. For the purposes of speed, first hour I made them get their calculator out, they had to add it, and it took some time. And I actually did it over here. Believe it or not, we got comma, 15 million total people in this state, okay? So that's the first thing. You have to add up and get your total population of your country if we're going to do this. Now, there are, and then it's interesting historically, when there was 13 colonies turned into 13 states, the number of representatives was smaller. So as we got as a bigger country, they decided we need more representatives, and that number would bump up as the country grew. But for this one, they decided their legislature is 300 seats. So the standard divisor, and then you can put off to the side what this means, is your total population divided by how many representatives or legislators there are. And what this number means is what I wrote over here. So if there's 300, I'm just going to use the word representatives, and there's 15 million people, that means for every 50,000 people, you should get a representative. Now, according to our book, unless my reading and memory from when I read this is wrong, it's pretty close for the state of, or the United States. I think it's like 54,000 something at the time the book was written, which still was in the 2000s. It's not like an ancient book. Okay, so very similar. So that's what the standard divisor is. You need to know that. Finding the standard divisor is really finding out how many people per representative for this situation. Okay, since you have this already printed for you, I can move on. What's the standard quota then? Well, it's taking the state's population, the individual state's population, and dividing it by the standard divisor. Now, why would we do that? Why would we divide this by 50,000? Let's make sense out of this. What does that simply do when I put 50,000 into state A's, dividing that into there? It tells me what? How many reps they deserve. Okay? So basically, they take all these numbers and divide it by 50,000, and then that's their quota, meaning that's how many representatives each state should get. Now, unfortunately, for first hour, I made them do all that dividing and tell me the numbers. This is first hour's numbers, so I hope they're all right. I had one person do it and one person discount double check it. And then here lies the problem. The problem is only in the decimals. Can I put 25.1 representatives into state A? No. So now we need a way to fairly figure out the fractional parts, is what they call it, even though I'm going to call them decimal parts. How do we fairly assign these decimals? What do we do about this? And then, of course, one state will be mad if they get one less representative than someone, or someone else gets it and they don't. So that's why there's these different methods. And then I'll tell you, as we go through it, what at least one of these methods favor. Okay, so any questions so far? I think this method is listed first because I think historically this is what was done first. And it's a pretty simplistic thing to do. And it seems to make the most sense. This is already what we done did. You find the standard divisor. We just did that for this with this country. And then we just determine the standard quota for each individual state. Now, each state must at least get one seat. I don't know if a state was ever so small that they got a decimal that was under 1. So we do have to make sure that that occurs. So do put a note to that. No matter what happens, you at least better get 1. You got to be represented in some way, shape, or form. All right, so what they get is their whole number. This is how many seats they get. But then we got to do something special with the decimal part. And you already have this listed down, so you don't have to write anything. Now, how do we assign the leftover seats? So what we do is we begin with the largest fractional parts. And what we do is assign those largest fractional parts these extra leftover seats. And it won't make sense until I actually do this example again. Okay, it's a new one though. Okay, so we start distributing to the state the biggest fractional part. One thing I didn't make you understand though is there is some leftover senators. When we round down all the decimals, we're going to have extra senators. I keep saying senators, it should be representatives. So then those extra representatives get assigned to the biggest fractional parts that are left over. This is the Hamilton method. This is one way of doing this. Today's is simple. When we get into tomorrow's Jefferson method, we might have an issue. That reminds me. So let's make sense out of all those words. I feel like I kind of jacked up some of them just to get you, in the right mindset here. Luckily, they do the math for us. The population's 18 million. So if you were to added these up, that should be 18 million. Okay? If it doesn't have that, you have to add those numbers up and get the total population like I did in problem 1. Then what we need to do is get the quota. Okay? So what we need to do is take this 60,000 and divide all of these by 60,000. It's real stimulating in first hour. I made first hour do it, and it took like 4 minutes. Okay, well, we'll take their numbers for you. Boom, and because this one's easy, I already have the answer written how the leftovers are taken care of, but I don't have something written. What you need to do is round all of these down, even to 43.916. That means they get 43 representatives, 72. I don't care that this rounds up. You just break it down to the nearest. This is actually called the greatest integer function, which makes no sense when they say that. Remember that? Greatest integer function means go to the smallest integer between 82 and 83. Anyway, that's a math term. When you add these up, I believe first hour we got 297. Go ahead and add those numbers, 72, 43, 82, 50, 50. All right, and see that you get that number. So we lost 3 representatives by rounding down. Now what we do through the who method, what's his name? Hamilton, and it said up there who Hamilton was. It was Alexander Hamilton. Since there's 3 senators, sorry, I keep saying that, so actually representatives or legislators. The first one that gets one is this 0.96 because it's the highest fractional part. So they get an extra one. Now that's 298 representatives. There's 2 left over. The next highest fractional part, decimal, is what I like to say, is this one. And there's one left. The last one is this one. 72, 44, 83, 51, 50. And now this adds up to 300, and all 300 are assigned to a particular state. So again, this is just one idea. It's the most simple, most direct to do this. Now some might say, why don't you just round up every time? Well, look at the letter E. Wouldn't letter E round up to 51 as well? Now you'd have 301 representatives. So that's why they did something a little different. A way to ensure that they use only the 300 that's allowed. Yawning! Sorry. Now, and again, I thought this was helpful to actually just yank out of the book. What happened? We're losing people. Okay, it's anarchy. All right, the Lowndes method comes from William Lowndes from South Carolina, which I do believe is a smaller state. So listen to what I have to say here. Okay, so this is the other one for the day. And again, you can highlight this or do whatever you want. I just wanted you to, see what we see in the reading about what his idea was. What if I had a state who had a standard quota of 1.5, fumble, 2 people, and another one that has 10.5? Well, these are equal, right? Equal decimal parts, fractional parts, correct? Yes, Mr. Samuelis. So what he decided was, all right, it makes a much more of a difference for the state that has 1.5, because that 0.5 fractionally compared to the 1 senator or representative they get, I keep saying senator, I'm so sorry, fractionally is much more significant than this 10.5. So if I gave this the extra representative, they get 11, and they would still only get 1. It's more important for the smaller state to have 2, and the other one still have their 10 and still be strongly represented. So what he made a big idea about was that fractional part should be relative to how many representatives you already get. So he devised a formula where you take that fractional part and divide it by how many representatives you get and analyze that decimal. And if that decimal is higher than some other states, they should actually get the representative, not the bigger state. So actually his method favored smaller states that had less representation. They more than likely would get the extra representative through his process. So this is called, this little dividing the decimal by how many senators, relative fractional parts. So he was more concerned about the relative fractional part as opposed to just who has the higher decimal. Right? Relative to how many representatives you already get. So we can do the same exact problem, but do Lowndes' apportionment method as opposed to Hamilton's and see if there's a difference. And there happens to be a difference. So again, his favors the smaller states because we're looking at relative to how many you already get. What does your fraction mean compared to somebody else? Okay, so here it is, and you can see this. I just snapped that previous example because these first two steps are the same as example 1. This is what we're going to do all the time. We're going to get our standard divisor, total population divided by the number of representatives. Then we're going to get our standard quota, your state's individual population divided by the standard divisor, to figure out how many representatives you have. Then after that, you analyze the decimal part. So this is exactly like the last example. You do step 1, add all these up. You didn't have to, though. We told you the population total. Get the standard divisor, calculate the standard quotas. But now we're going to do, is it Lowndes? I already forgot his name. Well, obviously, we do this again. So fine, they get 72, they get 43, they get 82, they get 50, and they get 50. Add this up, we've only assigned 297 representatives. It's exactly the same as the last question. But how we figure out how to give away the next 3 goes about dealing with this relative fractional parts. What is this decimal compared to how many you were already getting? So what we do is take that fractional part and divide it by how many you're already getting. Whoops. Now I will ask you to do that for my calculator purposes. Get your calculator out. Get your calculator out. Nobody's moved right now. That's the support I get in this class. And then I'll ask you what these little decimals are. So again, just to, before I go offline and before I get those numbers from you guys, be ready to tell me what they are. This is to see what their decimal part is in relation to how many they already get. All right, and then we analyze this decimal, and then we assign the extras. The highest relative fractional part will get the first representative, and then we go down the line from there. And that's what it ensures. What is this in relation to how many you already get? It favors the smaller numbers, which in fact is the smaller states by population. Now, this is the relative fractional part. This is what we're going to analyze by who gets the leftover 3 senators. The first thing is not a change. Sure, this is almost 44. So even relative to 43, this is our biggest decimal. So they will get an extra representative, 43 plus 1. No change. That's what happened in the previous example. I could show you that. What's the next highest fractional part? Who? A, B, C, D, or E? D, right? 0.014. I don't know if that was a 1 or a 2. People always ask, where do I round? Well, look at how small these decimals are. You want to take those out pretty far until you see who's bigger than who. And be careful on rounding errors. But that one gets 1. That is no different than using Hamilton's method. So these 2 states did not change. Who gets the last one? E. Now that's the difference. Just by doing this a different calculation, this state gets the last extra one. I think in the previous one, I forgot who got it. I think it was 82 got 83. Right? I could look up there. 82 got 83 instead. And that's the whole point. Just doing this a different way, we actually gave a representative to a smaller state because the other state already has 82 representatives anyway. And I'm sure this is what was in Lowndes' mind when he devised this little method. So mathematically, it's not really a big deal. It just takes a little bit of time. Okay?